Welcome to Machine Learning with Pats, your gateway to the world of artificial intelligence and machine learning. I'm thrilled to have you join me today as we dive into the exciting world of AI/ML. In this video, we'll be exploring a hands-on lab practical designed specifically for third-year mechanical students at Pune University. Our journey begins with the essential skill of acquiring, visualizing, and analyzing datasets, which is aimed at lab session number 2. It's a crucial step in the realm of AI and machine learning, and today, we'll explore it one by one. Whether you're a student, an aspiring engineer, or simply someone curious about the intersection of mechanics and AI, you're in for a treat. So, buckle up, hit that subscribe button, and let's learn together. In today's video, we will begin with defining aim and objectives. Each section will demystify terminology, outline our methodology, and guide you through the hands-on process of exploring datasets. By the end, you'll not only have a clearer understanding of AI/ML in the context of mechanical engineering but also gain practical skills in acquiring, visualizing, and analyzing datasets. Join me as we bridge the gap between theory and application in this exciting field. Let's start with defining our aim. It can be defined as, to equip students with the skills to acquire, visualize, and analyze datasets for machine learning applications aimed at condition monitoring of a triplex hydraulic pump using pressure signals. To reach to our aim, 3 distinctive objectives can be considered. First objective is familiarize students with the acquisition of pressure signals from a triplex hydraulic pump. Second is develop skills in data visualization and analysis using Python and relevant libraries. And last is enhance students' ability to draw meaningful conclusions from the analysis and make informed decisions. Before we explore any dataset, it is important to understand the end-to-end methodology. It begins with understanding the data acquisition. The first approach could be data collected through an experimentation. For this, you need to physically set up the triplex reciprocating pump in a controlled environment. Then you need to attach pressure sensors strategically to measure variations in pressure during pump operation. Lastly, you can utilize data acquisition systems to record pressure signals over time. The second approach could be data collected through simulations. Here, you can use hydraulic simulations to generate synthetic pressure signal data. Simulations can mimic different operating conditions and fault scenarios. There are some standard sources available such as multi-class fault detection using simulated data by MATLAB Simulink. The link is provided as below. The third and last could be use of benchmarking public datasets. Here you can explore online repositories or databases that provide pressure signal datasets from similar pump systems. You can use datasets available from PHM Society Data Repository, NASA Prognostic Center of Excellence, PCOE, UCM Learning Repository, SECA Manufacturing, etc. Once the data is collected through any of the approach discussed in previous slide, we move to the next phase of data visualization. You need to load the dataset in suitable software to explore more information about it. Suppose if you are working in a Python environment, you need to use the pandas library to load the acquired dataset. Once you load the data, you can display its information in various terms. You can also check for missing values and outliers that may impact the analysis. The next important step is visualization with Matplotlib and Seaborn. You start creating time series plots to visualize the pressure signals over the entire duration of data collection. Then you can generate histograms and density plots to understand the distribution of pressure values. Further scatter plots can be utilized to identify any trends or patterns in the data. Lastly, visualizing the correlation matrix would assist you to understand the relationship between different classes. This identifies potential dependencies and correlations in the data. Now let's explore some dataset. Here we will consider this example by MATLAB, which shows how to use a Simulink model to generate fault and healthy data. The data is used to develop a multi-class classifier to detect different combinations of faults. The example uses a triplex reciprocating pump model and its leak, blocking, and bearing faults. The CSV file titled raw simulated data.csv has this raw dataset. In the second picture, you can visualize the time intervals in the first column and corresponding pressure values for different conditions of a triplex hydraulic pump in further column. Each row represents a specific time point, and the columns represent different scenarios or states of the pump such as healthy and various faulty conditions. Here's a general description of the CSV file. First column has time values at which the pressure readings were recorded. First column has readings for the healthy condition of the pump. Column No. 2 to 8 have pressure readings for 6 different faulty conditions of the pump, that is from faulty 1 to faulty 6 in a sequence. Let's understand the data characteristics. The values in each column are numerical, representing pressure readings. Dataset appears to have a time series structure, with pressure values recorded at regular time intervals. The pressure readings vary over time, and different fault scenarios exhibit distinct patterns. Healthy readings are presented as a baseline for comparison with faulty condition. Once you download and understand the dataset, go to the next phase of load and explore the dataset in suitable software. Here we will use the Pandas library to load the acquired dataset into a Python environment. We will then try display the first few rows of the dataset to inspect its structure. The code can be found in the picture below. In the next slide, code is explained line by line. The first line of code, that is, import pandas as PD, imports the pandas library and gives it the alias PD. Pandas is a powerful data manipulation and analysis library for Python. As we are aware such common convention when working with pandas to make the code more concise. The next line, file_path equals raw simulated data.csv, creates a variable named file_path and assigns the string raw simulated data.csv to it. This string represents the file path or filename of your CSV file. Make sure the file is in the correct location or provide the full path if it's in a different directory. Next line of the code, df equals pd read_csv, file_path, uses the read_csv function from pandas to read the CSV file specified by the file_path variable. The function returns a data frame, and it is assigned to the variable df. The data is a two-dimensional, tabular data structure in pandas. Lastly, print df.head prints the first few rows of the data frame using the head method. The head method is useful for quickly inspecting the structure and content of the data frame. By default, it displays the first 5 rows, but you can specify a different number inside the parentheses if you want to see a different number of rows. Now if you would like to know more about the dataset, you can use description equals df.describe, followed by print description. This line uses the describe method to generate summary statistics of the numeric columns in the data frame. The result is a new data frame containing count, mean, standard deviation, minimum, 25th percentile, median, 50th percentile, 75th percentile, and maximum values for each numeric column. The new data frame is assigned to the variable description. Print description line prints the summary statistics generated by the describe method. This information gives you insights into the central tendency and spread of the numeric data in your dataset. If there are non-numeric columns, they will be excluded from the description data frame. Further, if you want to get an overview of the entire data frame, including non-numeric columns, you can use the info method. Print df.info line prints information about the data frame using the info method. This includes the data types of each column and the number of non-null values. It's helpful for understanding the overall structure of the dataset and identifying any missing values. Maybe you can also check for missing values in your dataset by using the isNull method followed by sum. To identify potential outliers, you can visualize the distribution of numeric columns using box plots. So df.isNull creates a data frame of the same shape as df, where each cell is true if the corresponding cell in df is null and false otherwise. Sum then calculates the sum of true values along each column, resulting in the total number of missing values for each column. The result is stored in the missing underscore values variable and printed. For outliers, check df. Select underscore types, include sad face, float 64, int 64, selects only the numeric columns from the data frame. The selected numeric columns are then used to create box plots using boxplot, vert equals false, to visualize the distribution and identify potential outliers. plt.show function displays the box plots. By running the code, the selected numeric columns were used to create box plots as shown in this slide depicts the distribution and identify potential outliers. Once you load the dataset in Python environment, the best way of understating the dataset is the visualization. The code shown in the slide creates time series plots to visualize the pressure signals over a time duration of data collection for various conditions. Explanation of the code can be found in the next slide. You can import the libraries and load the dataset using usual methods. Since I want to visualize the first 2000 points of the dataset, I will write next line as df_subset equals df.head 2000. It extracts the first 2000 rows of the data frame, df, and stores them in a data frame called df_subset. Moving ahead, I want to extracting data from various columns. Time equals df_subset, time, extracts all data points from column 1 that is titled as time. Further healthy_data equals df_subset, healthy, extract data points from column 2 that is titled as healthy. So accordingly, these lines extract specific columns, time, healthy, and faulty 1 to faulty 6, from the df_subset data frame for plotting. Now how to plot the dataset that has been extracted? Start with creating a new figure for the plot with a specified size of 10 inches in width and 6 inches in height using plt.figure, figsize sadface 10, 6. The figsize parameter is optional and allows you to control the dimensions of the figure. The plot function is used to create a line plot. The first argument, time, represents the x-axis values, and the second argument, healthy_data, represents the y-axis values. This line is plotting the variation of pressure over time for the healthy condition. The label parameter is to healthy, which will be used later for creating a legend. plt.label, time, seconds, and plt.alabel, pressure, kPa, set the labels for the x-axis and y-axis, providing information about what each axis represents. Similarly, plt.title, title of the plot, providing a brief description of the content of the plot. The legend function is used to display the legend, which in this case, will show the label healthy. The legend helps identify which line corresponds to which dataset. Finally, plt.show displays the plot. Without this line, the plot would not be shown. The show function is necessary to visualize the figure created earlier. The plots which are visualized after running the code can be seen here. The first plot shows how a pressure varies with respect to time when the pump was healthy and there was no any fault. Second plot similarly shows the variation of pressure over a time when pump was suffering from faulty type 1. However, variation between these two conditions cannot be examined just plotting the raw data in time domain as shown in these pictures, and thus we need some assistance. Similar to previous slide, the plots shows the variation of pressure over a time when pump was suffering from faulty type 2 and 3 in picture 1 and 2 respectively. The abnormal variation for fault type 2 can be visually perceived, however same is not true for fault type 3. Now when we visualize plots for fault type 4 and 5, a trend is clear. The fault type 4 shows declining trend and type 5 shows an increasing trend. Same is also true for fault type 6 as it shows a very abrupt changes perceived from sudden increase and decrease in the trend. However, comparing all the cases and making decision based on visualization is not possible. Thus we need some techniques to quantify the difference between various classes. There is another way of visualization to perceive some information on raw dataset trends. Here, instead of plotting separate graphs for individual classes, We will compare the healthy data with each of the faulty conditions one by modifying the code as follows. Let's start with defining a list named faulty_conditions containing the names of faulty conditions, specifically faulty 1 to faulty 6. The subsequent for loop iterates through each element, faulty condition, in the faulty_conditions list as for faulty_condition in faulty_conditions. Inside the loop, the code extracts the data corresponding to the current faulty condition from the data frame df. Here, df, faulty_condition, selects the column in the data frame that corresponds to the current faulty condition. This creates a pandas series, column, named faulty_data containing the pressure data for the current faulty condition. While creating a plot comparing healthy and faulty data over time, start with figure creation. plt.figure, fig size sadface 10, 6, creates a figure for the plot with a specified size of 10 units in width and 6 units in height. This sets the dimensions of the plot. plt.plot, time, healthy_data, label equals healthy, plots the data for the healthy condition over time. The label parameter is set to healthy for this line. And lastly plt.plot, time, faulty_data, label equals faulty_condition, plots the data for the faulty condition over time. The label parameter is set to the value of the variable faulty_condition. By running the code, you will be able to see the comparison of time series plots for healthy versus other faulty conditions one by one. In this slide, first plot depicts comparison of healthy pump and same pump with fault type 1. Similarly in second plot, it is compared with plot type 2. This representation slightly gives better understanding of variation of pressure amongst different classes. Look at the first plot. It depicts comparison of healthy pump and same pump with fault type 3, and in second plot comparison between healthy pump and same pump with fault type 4 is shown. In the same fashion, the comparison can be undertaken for all fault types. This can be considered as better way of visualization. However, while time series visualization is a valuable exploratory tool, it may not always be sufficient to uncover the complexities and nuances present in diverse classes of data. Complementary analytical techniques, such as statistical analyses, machine learning models, or domain-specific expertise, may be necessary for a comprehensive understanding of the underlying patterns and relationships within different classes. Now we will explore a few other data visualization methods. Let's start with histograms. Creating histograms to understand the distribution of pressure values for healthy and faulty conditions of a pump can provide valuable insights into the pump's performance and help in identifying potential issues. Histograms are graphical representations of the distribution of data, and in this context, they can be used to visualize the pressure readings under different conditions. Here's the code that you can use. After running the code, you can see the histograms for various conditions. The x-axis of the histogram represents pressure values, while the y-axis represents the frequency of occurrences. This allows you to visually compare the distribution of pressure values for healthy and faulty conditions. Analyze histograms to gain insights into the pressure patterns is the next step. Look for differences in the distribution of pressure values between healthy and faulty conditions. For example, which condition shows a relatively stable and centered distribution, and which one exhibit irregularities, spikes, or shifts in the pressure distribution. Histograms can help identify anomalies or patterns associated with specific faults. Unusual peaks, gaps, or shifts in the distribution may indicate issues that need attention. This visual representation makes it easier to spot abnormalities compared to just looking at raw numerical data. Our next method is KDE, that is kernel density estimation. It is a nonparametric technique used to estimate the probability density function of a continuous random variable. In the context of pump pressure analysis, KDE can be employed to visualize the distribution of pressure values in a manner similar to histograms. The ready-made code is given below. Here, instead of dividing the data into bins as in a histogram, KDE estimates the probability density at each data point. It uses a kernel, smoothed function, placed at each data point and then combines them to create a continuous, smooth density curve. The result is a smoothed curve that represents the underlying probability density of the data. This curve allows for a more nuanced understanding of the distribution of pressure values under different conditions. Let's compare both the methods. Histogram represents data using discrete bins, providing a step-like visualization. KDE produces a continuous, smooth curve, offering a more refined representation of the data distribution. Histogram is sensitive to the choice of bin width, which can impact perceived shape of the distribution. KDE is generally less sensitive to parameter choices, providing a more robust estimation of the underlying distribution. Histogram is clear for identifying general patterns and trends, especially in discrete data. KDE offers a smoother representation, for detecting subtle variations and capturing the overall shape of the distribution. How is KDE more advantageous than histogram? Point number 1. KDE provides a smooth representation of the data, reducing the impact of random noise and providing a clearer view of underlying trends. Point 2 is related to representation. The continuous nature of KDE allows more detailed understanding of the distribution, especially when dealing with continuous data. This can be beneficial when trying to identify patterns or anomalies. Point 3 is about bin size dependency. Histograms require the choice of bin sizes, which can affect the interpretation. KDE does not have dependency, making it more robust in certain situations. And last point is improved visualization of density. KDE provides a more accurate representation of the probability density function, making it suitable for scenarios where a finer analysis of the distribution is needed. We come to the conclusion now. Today's video is all about understanding acquisition and visualization of the data set when it comes to pressure signal datasets. We've covered the entire spectrum, from acquiring and visualizing the data to in-depth analysis using Python, with a focus on pandas, matplotlib, and born. The key takeaway is not just proficiency in these tools but the ability to draw meaningful insights, empowering you to make informed decisions in various scenarios. Now, for those eager to take the next step, I recommend applying these skills to real-world datasets, pushing your boundaries and problem-solving abilities. Additionally, delve into advanced machine learning techniques for condition monitoring, a frontier that adds a predictive edge to your analytical arsenal. Finally, don't forget the power of collaboration. Sharing your findings not only contributes to the collective knowledge but also opens doors to fresh perspectives and innovative approaches in the ever-evolving landscape of data science. Let's dive in and explore the exciting possibilities together. Appreciate you watching the video. Your support means a lot. Stay tuned.